All right, folks, we should be pretty much ready to roll here. So what I want to do today is to move forward with this idea of Lewis structures. So if we go back and think about the video that we looked at last night, and hopefully everybody had a really good mini break, if you can call it that. I know I did. I left town. Basically, what we want to do is expand on this idea of atomic Lewis structures to see what happens when we actually form bonds. Okay, so we're talking about two atoms or more atoms coming together to form one or more bonds between them. All right, so for example, we can talk about, for example, ionic Lewis structures. So we're talking about, in the situation here, ionic bonding here. Now, in an ionic bond, we're talking about something like sodium chloride, NaCl. All right. Now, you guys will probably remember when we talked about ionic things, we said that the reason why the bond forms between, for example, a sodium ion and a chloride ion is because each one carries a charge. So remember, the sodium carries a 1+ charge and the chloride carries a 1- charge. And it's those two opposite charges of the two ions that attract each other and hold these two things together in an electrostatic sense. Positive and negative charges attract each other. All right, but we could also show this in terms of a Lewis structure. Okay, so if I talk about just a regular sodium, let's just draw a Lewis structure for a regular sodium atom. Okay, it looks like this. It's a group 1A, so it carries one electron. And we saw how to assign that electron in the video. Now, I could also have chloride, or in this case, a chlorine atom, let's say, and it's over in group 7A. So as the video showed, it carries 7 valence electrons. Okay, so remember, the main group number tells you the number of valence electrons that the neutral atom carries. All right, so that's what sodium atom looks like, and that's what chlorine atom looks like. But if I want to make sodium chloride, remember, these things now are in the ionic form. And what drives us to get to the ionic form? Well, we want each one of the ions, as you guys will recall, to look like a noble gas, right? So the easiest way for sodium to look like a noble gas is to lose that one electron to go backwards and look like, I think it's neon. Yep. And for chlorine to actually gain an electron to move to its next nearest noble gas, which is argon. Okay, so basically, sodium wants to look like neon. Chlorine wants to look like argon. So sodium has to lose an electron to get that 1+ charge. Chloride has to gain one to get that 1- charge. So we kind of know what ends up happening here. I'm going to take this electron from the sodium and I'm going to give it to the chlorine. Okay, and that satisfies that requirement. So now that ionic bond can form. So what I'm going to have now is a sodium ion, and it's going to have around it a chloride ion with a 1- charge, and I'm going to put that octet or set of 8 electrons around the chloride. Now, what we normally do is we would put a set of brackets around that to show that the chloride ion actually owns all 8 of those electrons. Okay, so that's actually how we would make an ionic Lewis structure to show that ionic bond between sodium ion and chloride ion. All right. So in this case, we don't have any electron sharing going on. It's really a thieving of an electron so that each one of these things can look like its nearest noble gas. All right, so that's what we have. But the other option is to look at covalent bonding. So in the case of covalent bonding, you guys might remember that electrons get shared instead of stolen. So electron sharing is occurring. Now, covalent bonding, as you guys might remember, occurs between nonmetals. So it's a nonmetal plus another nonmetal. And remember, nonmetals are those things that are over on the right-hand side of the periodic table. Metals tend to be over on the left-hand side of the periodic table. Okay, so this is all stuff that we talked about way back when we first started talking about, for example, identifying formulas for compounds and learning how to name them. So remember, we had to identify whether something was ionic or covalent so we could figure out how to name it. So this is kind of just falling back on that situation. So a really simple example of this, and we may have actually done this in the video, I don't remember, is that I could have, for example, a hydrogen atom, which carries a single valence electron, and another hydrogen atom that has a valence electron. So we know that each one of these has a 1s1 configuration, okay? But what are we trying to do? Well, we'd like for each one of these hydrogens to look like a helium, right? That's always our goal, is to make each element look like a noble gas, because that's how we know it's stable. So given that these are both nonmetals and not one of these hydrogens wants the electron any more than the other hydrogen, rather than having one hydrogen strip the electron from the other, steal it, if you will, we're going to let them share. Okay, so what I'm going to do is I'm going to show a hydrogen, and then I'm going to have an electron pair, and then another hydrogen. And the idea here is now we can say that each one of these hydrogens at any moment can lay claim to that electron pair. If that happens, this hydrogen will be a 1s2 configuration, and the other hydrogen will also be a 1s2 configuration. And in each case, a 1s2 is a helium configuration. So we can say that each hydrogen looks like helium by sharing that pair of electrons. Okay? Does that kind of make sense to everybody? Any questions about that? And that's kind of going back and reviewing some old stuff, but just want to make sure we're all on the same page about that. So everybody's good? All right. So where I want to focus now is rules for constructing covalent Lewis structures. Okay, and we actually just did a real simple one right there with the hydrogen, with the H2. All right, so here's what the rules actually look like. First thing, and we're always going to fall back on these. Since we want to form some bonds, what we have to do is use valence electrons to make those bonds. So the first thing we have to do is we have to look at the formula of the thing that it is that we want to show the structure of, whatever the compound is, and we want to count up the total number of valence electrons of all atoms involved. So in the case of the H2 above, how many valence electrons have we got? Well, we've got a total of 2 because each hydrogen brings 1 in. So that's what we do. So that tells us that in terms of building blocks to make bonds, that's the number of electrons I have to work with. I can't have any more, okay? So the second thing is I need to choose the central atom. Who goes in the middle? Now, obviously, this is for molecules that are a little bit more complex than simple H2, where we actually can have an atom in the middle and other atoms radiating around it. Okay, so the central atom, the one that goes in the middle, has to satisfy 2 requirements. First of all, it's going to be the most metallic or metal-like atom. Okay, so it's the one that's closest to the metals generally in the periodic table. So in other words, if I'm looking at the nonmetals, it's generally going to be the one that's furthest to the left. Okay, the second thing is it can never be hydrogen. And the reason for that is because hydrogen can only accept 2 electrons to look like helium. So obviously I can't put more electrons in and around hydrogen than that. So it wouldn't make a very good central atom. Okay. Third rule. Now I'm ready to start making some bonds. So what I want to do is I want to use single electron pairs to form bonds out from the central atom. Outwards to the outer atoms. Those are the ones out around the periphery. All right. So we start using up electron pairs to make those bonds. One pair of electrons per bond. However, sometimes we run into a situation where we have extra electrons. So that's the next thing. If we have any extra electrons, what do we do with them? Okay, so again, we have a pecking order here in terms of where we put them. First thing is we're going to place them in pairs around the outer atoms. And we do this to satisfy the so-called octet rule. We want to put them around the outer atoms until all the outer atoms have an octet. That's 8 electrons, right? Then the other thing is if we have any around there anymore, after we've done that, we're going to place them on the central atom. Now, sometimes we need to do this to satisfy the octet rule for the central atom. But sometimes, as we're going to find out next time, we can end up putting more electrons around the central atom than 8, because there are certain atoms in the periodic table that can actually take an expansion of an octet. So we can put more than 8 electrons around there. But we won't run into any of those today. That's kind of an exception that we run into. And again, don't ever put the electrons around any hydrogens. If you have hydrogens around there, don't place any electrons around there. So I'm going to actually put except hydrogen here. So remember, hydrogen can only take 2, so we can't start sticking more electrons around it than we already have in a bond around it. Okay. So item number 5. Now we have to check that all non-hydrogen atoms actually have an octet. And remember, an octet means 8 electrons. Okay, so we're satisfying this thing called the octet rule. If not, then we actually have to provide octets. Now, we've only got a set number of electrons, so how do we do that if we've already used up all of our electrons? Well, we're going to do that by forming multiple bonds. And by this, I mean double bonds or triple bonds, and we'll see what those are here in just a bit. And that's always going to be around the central atom. And we only do this if we need to do it. Okay, so in many situations, we'll satisfy our octet rule without having to do that. But there are situations where we actually end up having to share more than one pair around the central atom to make sure that everybody gets that octet that it needs. Okay, so let's just do some simple examples and work through our rules and see if we can figure out how to do this. Okay, so here's a really simple example that is not just a simple diatomic. Probably the simplest example we can come up with is CH4, which is methane. Okay, so the first thing we want to do is count up the total number of valence electrons that we've got to play with, because that tells us basically how many bonds we can make. Okay, so carbon is in group 4A, so it brings in a total of 4 electrons. Hydrogen is in group 1A, so it brings in 1 electron, but hey, I got 4 of them, so I can multiply by 4, so that's a total of 4 electrons. Add those 2 up, and what do you get? You get 8 electrons total to work with. 4 coming from the carbon and 4 total coming from the 4 hydrogens that we got. Okay, so that's step number 1. essentially counting up the total number of electrons or building blocks that we've got. Okay, so the next part of this, let's just go back and review, is to choose the central atom. Now, in this case, it's very easy to find because we don't really have a choice. Can't be hydrogen, and the only other thing I've got going on here is carbon. So carbon's got to be the central atom. Okay, so I'm going to put the carbon in the middle, and I'm just going to array the 4 hydrogens around it, kind of like this. Okay, so the next thing, item number 3, says that we're going to use electron pairs to form bonds out from the central atom to the outer atoms. Okay, so I can go ahead and put those in. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I just made my bonds. All right. Now, another way I can write this, which I typically like to do just because it's faster to do, is I let an electron pair be like a dash. Okay, so another way I could write this, and this is the way I normally do it, is I actually end up letting each electron pair look like a dash, and that dash represents a chemical bond, a covalent bond. All right, so item number 4 says, any extra electrons? No, we don't have any extra electrons. We used them all up, so we can skip number 4. Now we have to make sure that everybody who needs an octet has an octet. So that's going down to item 5. Okay, so does carbon have an octet? Yeah, if you count up all the electrons around it, you're going to see that it has 8 electrons. So we satisfy the octet rule for carbon. Are the hydrogens happy? Yeah, they are, because remember, the best a hydrogen can do is a pair or a duet to make it look like helium. Okay, so each hydrogen has its pair of electrons to look like helium. So we're done. There's nothing else we can do here. Okay, so any questions about that? So we're basically just following down through the rules until we end up getting where we need to get. Everybody all right with what we did there? And again, it's important, just like any other rules we do here, to basically follow this in the sequence I give you. Okay, it doesn't help to jump around. So let's do another one. Let's do CF4. That's carbon tetrafluoride. Non-metal, non-metal, so it's still covalent. So let's count up the number of electrons. Carbon's group 4A, so it's going to have 4 electrons. Fluorine is over in group 7A, isn't it? Okay, so that means I've got 7 electrons per fluorine, but how many of them do I have? Well, I got 4 of them. 4 times 7 is 28. So the fluorines are bringing in a total of 28 electrons. Add that to the 4 from the carbon, I get 32. Okay, everybody see where that came from? All right, who do you think goes in the middle in this case? Because I don't have hydrogens now, so I have to kind of pick something that goes in the middle. So who is the least, or I should say the most metallic thing here? The thing that's closer to the left-hand side of the table, carbon or fluorine? What do you guys think? I'll give you another hint. In many situations, they'll actually in the formula put the central element first in the formula. So that would suggest it's going to be carbon. And indeed, if you look at a periodic table, carbon lies to the left of fluorine. So that tells us that it's going to be in the middle. So we're going to put it there. Go ahead and put the fluorines around it. We need 4 of them. Let's make our bonds. Okay, so I'm going to go ahead and use my dashes just because it's faster. 1, 2, 3, 4, 5, 6, 7, 8. I've used 8 of my 32 electrons. But now, where do I go next? What does the rule say? Any extra electrons, that's rule number 4. It says place them in pairs around the outer atoms to satisfy the octet rule, except for hydrogen. Don't have any hydrogens, so we're going to put them around the fluorines. I've used 8. We'll just use pairs here so you can see them. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Looks like I used them all up, didn't I? Okay, so all of my 32 electrons have been used. So now the next thing we have to do is make sure everybody's got an octet. Carbon looks like it has its 8 electrons around it. 4 pairs is 8. All the fluorines are equivalent, right? So count them up. looks like I have 1, 2, 3, 4, 5, 6, 7, 8 around every fluorine. So I've satisfied the octet rule around everybody. Okay, so do I need to do anything else? No, I'm pretty much done here. That's the best I can do with this. All right. Any questions about that so far? Everybody okay? Let's do water. All right, so again, count up the total number of electrons. Hydrogen brings in 1 apiece times 2. So hydrogen is going to bring in a total of 2 electrons. Oxygen here will bring in, what group is it? Looks like group 6A. So it's going to bring in 6 electrons. So I've got a total of 8 electrons to play with here. All right, so next question, who goes in the middle? Well, again, in this case, we know hydrogen can't. So that's going to dictate that oxygen has to be in the middle. Okay, so I'm just going to put hydrogens around it. 2 of them. Make some bonds. 1, 2, 3, 4. Oh, but I still have 4 more electrons of my 8 left to go. Can I put them around the hydrogens? No, the hydrogens are happy. They both look like helium, right? But where can they go? We got one more option, right? Got to go around the oxygen. So I'll put them on there as, again, non-bonding pairs. Check for your octet rule. Okay, oxygen looks like it has its 8, so it's good. Hydrogen has its duet in each case, so it's good. So do I need any double bonds, triple bonds? No, I don't. I'm good. I got everything exactly where I want it. All right. So far, so good. All right, guys, any questions about what I've done here with these 3 examples? Hopefully you see how I'm just kind of working sequentially through these rules that I gave you. Okay, and so far some of the rules we haven't even had to use yet. These are the simple ones. Questions?
Question.
Go ahead.
Oh, and the last one with the water, does it matter what side the hydrogens go on of the oxygen? Would it matter if one hydrogen was above the oxygen, the other one was to the right, or does it have to be horizontal like that?
Well, at this point in the game, when we just do Lewis structures, it doesn't really matter. Okay, if you wanted to do it at like a 90-degree angle, that would be okay. All right. What we're going to find out, and Chem 101 actually does this really well, is that once we derive Lewis structures for molecules like this, there's actually going to be a 3-dimensional geometry that kind of falls out of that. And then it starts to matter. But for now, it's fine to do it, however you want to do it. I generally do it symmetrically around the central atom just because it looks nice. Okay, it doesn't have to be that way. That's just generally how we do it. And I was just taught from day 1 to do it that way, just kind of arrange everything symmetrically around the central atom. But again, when we hit molecular geometries, okay, Lewis structure will dictate what those 3-dimensional geometries are going to look like. And then it starts to matter. But for now, not so much. Does that answer your question?
Yes, it does. Thank you.
Great. All right, so let's do another one. Let's do an ion. That's the nitrite ion, right? It's one of those polyatomics that you had to learn. Okay, so let's go ahead and do the normal thing here. Nitrogen's going to bring in a total of 5 electrons because it's over in group 5A. Oxygen's in group 6A, so that's 6 electrons. Oh yeah, but I have to multiply by 2 because I have 2 of them. So that gives me 12 electrons. And then there's one other thing here. When we're dealing with ions, if I have a 1- there, I got to add that extra electron in. So I'm going to go ahead and do that. Okay, so now I'm going to add them all up. 12 and 1 is 13. Plus 5 more is 18. Did I do my addition right? Hopefully I did. I think I get 18 electrons there. Okay, 12 plus 5 plus 1. All right, so now we actually do have to make some kind of an assessment of who goes in the middle. So again, the formula kind of hints you at it in this case. It says that the nitrogen should go in the middle. And if you consult the periodic table, you'll actually see that nitrogen lies a little bit to the left of oxygen in the periodic table. So that would make it a little bit more metallic. Okay, so that would suggest the nitrogen would go in the center. Now we'll put an oxygen around either side of it like this. And now we're going to go ahead and make some bonds, right? So the rule says 1, 2, 3, 4. Okay, but now I've got more electrons, right? I got 14 more electrons to play with. So the rule says if I have extra electrons, they got to go first on the outside atoms as long as they're not hydrogens. Okay, so I'm going to try to go ahead and apply the octet rule to the outside ones. So I've used up 4, 5, 6, 7, 8, 9, 10. Go to the other oxygen. 11, 12, 13, 14, 15, 16. Okay, so each of the oxygens now has an octet, but I've still got 2 electrons left to play with. So where's the next place you go after the outer atoms? Oh yeah, just a quick review here. Any extra electrons? A says go around the outer atoms. B says, all right, if there's any left over after that, we're going to place them in pairs around the central atom. So outside atoms first, then the central atoms. So now we're going to put that extra pair of electrons in here on the nitrogen. Okay. Now, the last thing that we know we have to do is we have to check and make sure we satisfy the octet rule for everybody. Okay, so if you look at the oxygen here on the left, yeah, that's got an octet. Look at the oxygen on the right. Yeah, that's got an octet. They're good. But what about the nitrogen? Count up the electrons around the nitrogen and see what you got. I see 4 bonding electrons and 2 non-bonding electrons. That's 6, right? So is nitrogen satisfied the octet rule here? No, it hasn't. It's 2 electrons shy of an octet. But I've used all my electrons up. So now what do? That's where we go back to that last rule. So it says check that all non-hydrogen atoms have an octet. And if it doesn't, then we want to look at forming multiple bonds, either double bonds or triple bonds around the central atom. Now what that means is that I'm going to share another pair of electrons to make another bond. And I'm going to have to share it out from one of those oxygens into the nitrogen to get the nitrogen in the octet. And I'll show you how I might do that. I might take that pair, for example, on that leftmost oxygen and share it back in to form another bond here. Okay, so now if I rewrite this, it might look something like this. Okay, so now I've got 2 bonds in here. Then the oxygen, since I shared that, now has those electrons around it that didn't get shared in. So now go ahead and count up everybody. Does the oxygen on the left still have 8? Yeah, sure. You get the 2 that are bonded in, 2 bonds into the nitrogen. That's a total of 4. Then you get 5, 6, 7, 8 from the non-bonding ones. That's good. Count up your electrons around the nitrogen. Bonding wise, you got 1, 2, 3, 4, 5, 6. Non-bonding, 2 more. That's 8. Check your oxygen on the right. You got your bonding, that's 2, plus 1, 2, 3 pairs of non-bonding, that's 6. 2 and 6 is 8. Okay, so what I've now got is an appropriate Lewis structure for nitrogen, or sorry, for nitrite ion. The one other thing that we sometimes do here, or would always do, is put it in brackets because it's actually an ion. And I would remind myself it's an ion by putting a 1 minus up there. Okay. So here's a question I've got for you. Is that the only way I could have distributed those electrons to make this work? Can you see another way I could have done it and still gotten everybody an octet? Do I have another option that I didn't use? Well, I see another option. I could have used the other oxygen, right? So another thing I could have done is I could have, for example, had this oxygen donate a pairing. That would have worked all right. Okay, so if I do that, here's what I have. Now the double bond goes to the other side. Okay, it's still a 1 minus. Okay. Now, this is interesting because now what I have are essentially 2 equivalent structures. These are basically the same, aren't they? If you look at it, the only real difference is just which oxygen I borrowed that second bond from. All right. So in a situation like this where I can draw multiple Lewis structures, I'm going to refer to these as resonance structures. All right, which is perfectly acceptable to do. Those are called resonance structures. So it just means there are different ways I can get those octets out to the atoms that need them by just putting, in this case, double bonds on opposite sides of the molecule. Okay, everybody see how I could do it either way? And in this case, these resonance structures are totally equivalent to one another. You can see that it's just absolutely symmetrical on both sides. All right, any questions about that? So we did two new things here. We showed multiple bonds here to get an electron deficient atom, an octet. And we also showed that there are multiple ways of doing it, which we now call resonance structures. Everybody good? Do one more, because this will involve some resonance structures as well. That's carbon dioxide. Okay, carbon brings in 4 electrons, group 4A, oxygen's group 6A, times 2, that's 12, plus 4 is 16. So I got a total of 16 electrons to work with. Okay, carbon's going in the middle because it's definitely to the left of oxygen in the periodic table. Put an oxygen on either side. Start using those electrons. 1, 2, 3, 4. Now we go to the outer atoms. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so notice now that the oxygens are happy, right? They've got their octets. But what about carbon? Is carbon happy? I'm only seeing 4 electrons around carbon, and carbon would really like to have 8. Now we're out of electrons, so the only option we've got is to make some multiple bonds. So what's one way I could do this? How can I get carbon its 8 electrons? It needs to get from 4 to 8, and I need to make multiple bonds to do it. So what's a way I could do it?
Make 2 double bonds.
Okay, so I could take, for example, an electron pair from there and an electron pair from there. That would be okay, wouldn't it? So now I would have carbon double bonded out to oxygen, carbon double bonded to oxygen. Then I would have 1, 2, 3, 4, 1, 2, 3, 4. So yeah, that's perfectly acceptable. Everybody has an octet that way, right? Now, is there another way I could have done it? Do we have options besides double bonds? Did I mention another option besides the double bond we could use? How about triple bonds, where you're actually sharing 2 pairs of electrons in from one of those oxygens? So now I can make something that looks like this. Okay, so now basically what I did was I brought in a second pair from that oxygen on the left, okay? And now if you count across, everybody still has its octet. And if I can do it that way, well, I could do it across the molecule too, couldn't I? Where I could make the triple bond on the right-hand side and the single bond on the left-hand side. So in this case, I have a total of 3 resonance structures that I could use. All right, so that's kind of nice. And your question next might be, okay, well, is there one resonance structure that's better than the others? And it turns out there is, and we can use this thing called formal charge to determine that, but that comes a little bit later. For now, it's good enough just to see there are 3 ways that we could do this. Okay, so we have 3 resonance structures, 2 of which are equivalent and 1 which is non-equivalent. All right, so the next thing I want to show you is I want to take us all into Chem 101 here, because Chem 101 has a really nice way of doing this. Okay, so let's just do one more here and we'll then show how to do it in Chem 101. Let's do NH3, which is ammonia, because that one's actually in the practice problems. Okay, so nitrogen brings in 5 electrons, 3 hydrogens, so that's 3 electrons. So that's a total of 8 electrons. Okay, nitrogen's got to go in the middle. We'll put our 3 hydrogens around it. Use up our electrons to make some bonds. 1, 2, 3, 4, 5, 6. And then the last pair goes on the nitrogen like that. Now, am I done? Yeah, I'm done. There's nothing else I can do here. Everybody who needs an octet has an octet, and the hydrogens have the duets. We're good. So let's run over to Chem 101 real quick and just take a look at how we can actually use the app in Chem 101 to make that Lewis structure. So I'm going to pop out of here for a second, go back into Chem 101. And let's just go to a real quick in class. And I need to generate a new set of problems for you guys. And I'm just going to start this. And we're going to do one of these together. Okay, look at number 5, guys. Everybody see that? Hopefully I should still be screen sharing here. It says draw the Lewis structure for ammonia, NH3. Okay, that's the one we just did. So now how can we do it in Chem 101? Well, Chem 101 has its own app that allows us to do this. So I'm going to go to this. There's the, you can see up there the actual Lewis structure, which is pretty much what we drew. Let's show the question. Okay, so here's what happens. When you go into the app, it says click to draw a new structure. So I'll click. Okay, so here we are. Now here's the deal. You'll see that you have a red dot and you got a black dot. The red dot's always where you're focusing. Okay, so in this case, we'll let that be the central atom, which is the nitrogen. And we can define that here in a little bit. But notice to the right, it says number of bonds. And I can, that's on a little slider. I can move that up and down. So see if I take that to 2, I get 2 bonds. And I need, in this case, 3 bonds. So I'm going to go ahead and run the slider up to 3. Now I can actually tell you what the elements are going to do. So see how there's a little periodic table on the lower right? I can click on that. And see the red one's my central atom. So I want to assign that nitrogen. So I'm just going to click on nitrogen. Oh, look at that. Now, let's go to that one. If I click on the top one, it goes red. So now I want that to be a hydrogen. So I'll click on that. Now I'll click on that guy, go back to the periodic table, tell it it's going to be a hydrogen. Click on that last one, go back to the periodic table, tell that it's a hydrogen. We're good. All right, so we're not done yet. We need to assign an electron pair. So again, it's worth going out and doing this beforehand, draw out the Lewis structure using the rules. And then once you've done that, come in and draw it here. Okay, I wouldn't do this on the fly. I'd figure it out first. But we know from our Lewis structure that we just drew, we need to have a pair of electrons on that nitrogen. So I'm going to highlight the nitrogen by clicking on it. And notice on the far left, you have electrons. So if I put that slider up to 1, there's 1 electron on the nitrogen, but I want more than that. I want to actually have a pair. So if I run the slider up to 2, notice that I actually end up with a pair of electrons on the nitrogen. And that actually ought to be the same Lewis structure that I gave you guys before. Okay, so there it is. So I can click done. And I could actually show the answer and it'll tell me hopefully that I got it right. Oh yeah, it tells me I got it right. Okay, so that's worth playing around with a little bit. So we have a few minutes. So go ahead and play with these a little bit. So I'm just going to run you back to the problems here. And some of these just deal with individual atoms, so you can play with that a little bit. And then some of them actually deal with covalence. If you want to run right to the covalent ones, you're welcome to do that. But go ahead and use the last few minutes we have to practice on this a little bit and practice with the app a little bit. It's actually very nice once you do a couple with it. And again, if you want to do another one together, we certainly can. Yep, nitride, number 2. Remember, that is N3 minus, guys. That's the nitride ion. Number 3 is an ionic one. That's good. Yep, looks like B is the right answer there. So if you look at the one I just projected, drawing the Lewis structure of Cl2, if you see the one that was incorrect there, the problems that you got with that one is, first of all, you need to define the right-hand atom as a chlorine. And then you also have to put the electron pairs around each chlorine to get the octets. So it looks like the one above it. So again, that's just getting used to how the app works. So what we're going to do next time, guys, is we're going to talk a little bit about some of the exceptions to the octet rule. So go ahead and look at the next video that we have, and we'll swing back around and look at some exceptions to the octet rule. And we're going to do a whole bunch of practice with this. So get to the point where we really want to get Lewis structures down and get used to the apps. We're going to do a whole bunch of practice next time around on this. All right, guys, I got 12:50. Continue to play around with this if you wish. And I will see you guys on Wednesday.
Professor, I just had a quick question.
Yeah, go ahead.
I'm leaving for a military training event on the 20th of May.